Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing unit number 11, lesson number 2 on horizontal stretching of functions. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes at the top of each worksheet. If you use your smartphone or a tablet, you can scan that code and you'll be brought directly to the video that's associated with that particular lesson. All right, let's begin. In the last lesson, we looked at vertical stretching and reflecting of functions across the x-axis. In this lesson, we're going to actually look at the horizontal component of that. Now this is considerably more tricky, just like horizontal shifting is. So let's get a feeling for it in the first problem. Exercise number 1. The function f of x is shown on the graph below. Selected points are shown as reference. The function g of x is defined by g of x equals f of 2 times x. Notice that the multiplication by 2 happens before f is even evaluated, and this is tricky. All right, but let's see how it works. Letter A says find the values of each of the following. Carefully follow the rule for g of x and show your work. All right, so watch. G of 2, here's my rule. Let me put it in big red. Here it is. There's my rule, all right? Remember, follow the function rule and you can't go wrong, okay? So, G of 2 is f of 2 times 2, right? I'm just putting in 2 for x. But that means G of 2 must be f of 4. Well, what's f of 4? 1, 2, 3, 4. Oh, it's 0. All right, so g of 2 is 0. Fine, whatever. All right, g of 3. Well, that's going to be f of 2 times 3, or f of 6. 1, 2, 3, 4, 5, 6. Ah, that's negative 1. Great. All right, g of negative 2, that's going to be f of 2 times negative 2. That's going to be f of negative 4. Well, let's see, 1, 2, 3, 4. 1, 2, 3, 4. Ah, all right. Think you have it? Pause the video and finish the last 3. All right, let's go through them. You might even be quick enough now to say that g of 4 is just f of negative 8. Right? Because it'll be 2 times negative 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. All right. G of 0 is going to be f of 2 times 0. I'm going to do this one out long ways again. And that's f of 0. And that's 1, 2. Okay, 2. And g of negative 3 will be f of negative 6. And that's 1, 2, 3, 4, 5, 6. And that's 0. Now letter B is pretty important. It says given the definition for g of x, the one that I've got in a box with stars by it, why can we not find the value for g of 4? Explain. Well, pause the video now and see if you can figure this out. All right. Well, again, as I've mentioned in a previous lesson, if they say why can't you find it, try to find it. Something will get in your way. So g of 4, using that formula, is f of 2 times 4. And that's f of 8. Well, okay. 1, 2, 3, 4, 5, 6, 7. Oh. Huh. I can't do that. Why can't I do it? Right? I can't do it because 8, x equals 8, is not in the domain of f of x, right? So, 4 is in the domain of f of x, but 8 is not. All right, letter C. Now, letter C is very, very important. It says state, because we're gonna graph G in a moment. We're gonna graph G, right? We gotta graph G. So we want some points on the graph of G. And letter C says state the points that must lie on the graph of g of x based on your work in A. All right, fine. But it's very important then that you understand inputs and outputs. So for instance, this point is the point 2, 0. Then we have the point -2, 4. We have the point 0, 2. We have the point 3, -1. We've got the point -4, -4. And we've got the point -3, 0. And I really want to emphasize that because I could see some people coming along and saying, you know, let's take this point, for example, saying, oh, I've got 6, -1. No, you don't. The input was 3, the output was -1. That F, that was just part of the rule. It's not the input-output pair. So these 6 points have, ooh, I went into the dark part of the screen. Those 6 points have to lie on the graph of g of x. All right, we're going to graph it on the next screen. So pause the video now if you need to and copy down anything you have to. All right, here we go. Let's do some graphing. All right, so letter D says graph the function g of x based on your work from B, then state the domain and range of both the original function f of x and our new function g of x. What remained the same and what changed? I'm going to go back to blue. So let's plot these points. 2, 0 is right here. 3, -1 right there. -2, 1, 2, 3, 4 right there. -4, 1, 2, 3, 4. -4. 1, 2, 3, 4. It's right there. 0, 2 is right there, and -3, 0 is right there. I think I'm going to connect these all with a nice blue line, or a set of blue lines. One is there to there, and one is from there to there. All right, take a look. Let me just make sure that we have it. Let's do this, the original f of x in red, and then since this graph is already in blue, we'll go g of x. I'm going to go back to red. Let's do some domain and range. Domain are the x's, 1, 2, 3, 4, 5, 6, 7, 8. So its smallest x is 8, and its largest x is 1, 2, 3, 4, 5, 6, or in interval notation, -8 to 6. Its range, its smallest y value, 1, 2, 3, 4, is -4. And its largest y value is 1, 2, 3, 4, +4. Interval notation, -4 to 4. Right? Now let's go into blue and let's do our new function. Well, its smallest x value now is -4. And its largest x value is 3, or in interval notation, -4 to 3. Its smallest y value, though, continues, look at this. Its smallest y value continues to be -4, and its largest y value continues to be 4. Out of room here, right? So this is cool. Take a look. So the domain changed. And the range stayed the same. Now, this is really crazy though. Again, I want to circle it in red. Look at how counterintuitive this is. When we took the input and we multiplied it by 2, the domain got squished by a factor of 2. That's a very technical term. It got squished. It got compressed. Every x value got divided by 2. In other words, this x value that was at -8 became this x value at -4, but the y values remained the same. This x value that was at -6 became this x value at -3. This one at -4 became this one at -2. Isn't that weird? So counterintuitive because you'd think, well, I multiplied the x values by 2, everything should get larger or wider by a factor of 2, and it doesn't. Isn't that similar to the horizontal shift? We add 3 to x, all of a sudden we shift it left 3 from your perspective, sorry. or we subtract 2 and we shift it right 2. Exactly the same thing here. Whenever we do something to an input as our first thing, it kind of works in the opposite of what you'd expect. And you'll investigate why that is a lot more in Algebra 2. For now, it's just something we want to get a feeling for and be able to use. All right, there's a lot on that screen, so pause the video now and write down whatever you need to. Okay, here goes the text. All right. Oh, letter E. I think we already did this, but let's write it out formally. Sorry, this is when I get ahead of myself. I do it all the time in class. My students hate it. So, describe what happened to the graph of f of x when we multiplied the function's input by 2. All x values got divided by 2 to produce the graph of G, which I just think is cool. It's really amazing to me, all right, that it works out that way. Also amazes to me that I can get as old as I can and as I am and not know to dot my I's. Anyway, whatever. So I'm going to clear this out, and then what we're going to look at is another example of this. Okay, here it goes. Let's take a look, because it's so weird that you want to make sure you see it a bunch of times. So let's take a look. In exercise 2, we've got the graph f of x equals the absolute value of x minus 3, shown on the graph below. The function g of x is defined by 1/2 times f at 1/2 times x, then the absolute value, then minus 3. So what I really want you to do is compare this formula to this one, right? Look at how similar they are, with one key difference. In this formula, we multiply x by 1/2 before we ever do anything else, okay? So what we're going to do is we're going to graph our new function, and we're going to do that by opening up the TI-84 Plus. All right. We want to go into y equals. Okay. We want to clear out anything that might be in y1, y2, etc. All right, take a moment. All right, let's enter that formula into y1. We want to be careful. First thing that we have to do is get those absolute value bars. Okay, and remind you how to do that. You hit the math button. All right, and the first thing you basically see is ABS, absolute value. So enter that. Now again, on the newer calculators like what I have, is it automatically brings up those absolute value bars, which is super duper cool. On older calculators like the TI-83 Plus, again, one of my favorites, you'll get ABS with a parentheses, okay? Make sure to put the other parentheses in once you've closed the absolute value bars. But for us, we're going to type in 1 divided by 2 times x. All right. Now what I have to do is I actually have to hit the right arrow, all right, in order to get out of the absolute value bars. Again, if you're on the TI-83, it would look like this. Now I don't want to forget to put the minus 3 in there, so let's do that now. Minus 3, and I'm going to hit enter. Now again, as always, check it over, make sure it looks good. Absolute value, those bars, 1/2 times x, it's all good. Bar, minus 3, okay. And now I want to go into my table, all right? Now as always, or my table setup, I'm sorry. I want to go into my table setup, and I have to figure out where to start the table. The key here is thinking about my graph paper. 1, 2, 3, 4, 5, 6, 7, 8. The minimum value on my graph paper is 8. The maximum is positive 8, so I'm making my table start at negative 8. So let's go into that table setup. Let's do it. All right, let's make table start at negative 8. And let's make the table go by ones. Okay. Now, check it over. Sorry, I feel like I'm moving too fast on this, and I don't want to do that. Now let's go into the table itself. So second graph, great. Now we don't have to write down every one of these points. We just want to write down enough of them. So for instance, I'll definitely start at the negative 8. And what it shows me is that I'm getting a y value of 1. I think I'll skip over the negative 7 because it's a decimal, but I'll maybe go negative 6. It's got a y value of 0. Negative 4 has got a y value of negative 1. Negative 2 has got a y value of negative 2. And 0 has a y value of negative 3. And then we start getting symmetry, the kind of symmetry we saw with parabolas, but now it's with absolute values. At 2, I'm at negative 2. At 4, I'm at negative 1. At 6, I'm at 0. And at 8, I'm at 1. And now I want to graph it, right? So I'm going to go out to negative 8 and then go up 1. Actually, let me erase this obnoxiousness here. So I'm going to go out to negative 8 and go up 1. Then I'm going to go to negative 6 and I'm at 0. 1, 2, 3, 4. Negative 1. 1, 2, 1, 2. 0, 1, 2, 3. Ooh, that didn't go anywhere. 2, negative 2. 4, negative 1. 6, 0. And 8, 1. I think we'll just use that line utility again. I love that thing. And slap some arrows on. All right. What was the effect on the graph of f of x when we multiplied the input by 1/2? Well, this is cool. Watch. Let me show you it. Here we had an x value of negative 3, but then that became an x value of negative 6. Right? Isn't that kind of cool? We could track another point. Here we have an x value of negative 2. That thing went over here to an x value of negative 4. So each x value on f of x was multiplied by 2 to get the x value or values on g of x. So again, it worked exactly counterintuitive to what you'd think. You'd think, oh, I multiply x by 1/2, yeah, the graph's going to compress. But it doesn't. It actually gets wider then, right? It stretches out horizontally. And this is, I think, one of the trickiest things in Common Core Algebra 1, this counterintuitive nature of what happens when you have a horizontal transformation. It's crazy, crazy, all right? So I'm going to clear this out. Pause the video now and write down anything you need to. Okay, here we go. Let's do one more problem. Maybe the hardest thing in function transformations is to put multiple ones together. All right, so what we're going to do in this last problem of the lesson is we're going to combine the vertical stretching that we saw in the last lesson with the horizontal stretching that we saw in this lesson. So let's take a look. We've got our favorite letter of function, f of x, graphed on this grid. All right, the new function h of x is defined as 2 times f of 3x. So 2 times f of 3 times x. Letter A says, evaluate h of 1. What point must lie on the graph of h of x based on this calculation? Why don't you go ahead and do that? Pause the video now. All right, well, follow the rule, right? H of 1 will be 2 times f of 3 times 1. So that's 2 of f of 3. Well, what's f of 3? Well, 1, 2, 3. Here's 3. 1, 2, 3, 4. So f of 3 is equal to 4. So I'll get 2 times 4, and that'll be 8. So that'll be the point 1, 8. Right? All right. But notice it was really based off of the point, right? It was really the point 3, 4 became the point 1, 8. Now I want you to think about that, okay? What happened? Well, the x value was divided by 3, but the y value was multiplied by 2, right? So whatever happens to y works kind of the way you'd think it would. So hey, I multiplied the overall function by 2, all the y values get stretched or multiplied by 2. But I multiply that x value first by 3, and all those x values get divided by 3. So the y values on f of x are multiplied by 2, and the x values are divided by 3. And it says graph g of x by plotting 3 major points. Now we already have one of them. 3, 4 ends up going to 1, 8. But let's take the other two. Let's take these two. So what's this point? It's 1, 2, 3, 4, 5, 6, negative 6, negative 2. Negative 6, negative 2. So what are we doing? We're taking the x value and we're dividing by 3. So negative 6 divided by 3 would be negative 2. And then we're going to take the y value and we're going to multiply by 2. So that will be at negative 4. And then let's do this point. Whoa, that's at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh. And the y-coordinate is at 0. So again, we're going to take this and we're going to divide it by 3. So 12 divided by 3 is 4. Now this is a little bit weird. With 0, when we multiply that by 2, it's still 0. So let's take the point. And let's graph, I think I'm going to graph this point first. I know that seems weird, but 1, 2, 1, 2, 3, 4. So that point went down there. All right, this one becomes 1, 1, 2, 3, 4, 5, 6, 7, 8. So that one went up there. And this thing way out there at 12, 0, 1, 2, 3, 4 just becomes 4, 0. All right, let me graph it in red just to make it really kind of bright and shiny. And look at that, right? And what's really happened to this graph is we've taken it and we've compressed it by a factor of 3, and then we've stretched it by a factor of 2. All right? That can be pretty tough to think about. Follow the functions rule. All right, so pause the video now, write down what you need to, and then we're going to finish up the lesson. All right, here it goes. So today, we saw horizontal transformations, and specifically horizontal stretches and compressions. You get those kind of things when you take the x variable, the input, and you multiply it by some constant before you do anything else. When you multiply by a constant greater than 1, ironically, it takes the graph and it compresses it. So if I multiply it by 2, then the original graph would have all its x values halved. On the other hand, if I multiplied it by 1/2, all the x values would be doubled. Again, this can be quite confusing, and you'll get more and more work on it as you progress in your mathematics. Not so much in this course because, quite frankly, we're in the last unit. All right. For now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.